Okay, so let me begin by asking for any questions from the previous session. Munib, you have any questions from the previous class? So can you summarize, let's say, in a couple of sentences what we did last time? Whatever is, in your mind. I want to see how much and what you have retained. Good. So that's really nice summary. What we did last time was study vector spaces. The next question is that why did we study vector spaces? So I'll again ask Munib. Well, I mean, why do you think we spend a whole lecture on vector spaces? And perhaps in many of the quantum physics course, you do that, right? So Abdullah, why do you think? So the main reason was this, that it's actually a fundamental law of universe. It's a little bit, and let me first say the law and then I'll give a few comments that the state of a physical system is represented by a ray in a Hilbert space. It's, the statement of this fundamental law, I mean, you can call it postulate, axiom, or law, whatever you want. It's very different from what you are used to studying in earlier classes, like, okay, the law of nature is Newton's second law, suppose, F is equal to ma. Or, the law of gravitation, or thing like this. But this law has a bit strange, wording, that we say that the state of a physical system is given by a ray in a Hilbert space. I mean, initially, at least it seems different, but when you go down and start thinking about it, then you see that it's essentially not any different from saying one of the laws of nature is this, that F is equal to ma. Then you might spend maybe a few lectures on explaining what is F, what is M, what is A, what are their properties, what type of mathematical functions can represent these quantities. For example, M is always positive, but at least in most situations, it's a scalar number. A is a vector, it comes from some second differentiable function, which represents displacement and so on. So to give, a mathematical statement for Newton's second law is something to say, okay, force, and then you define, what type of functions can be forced, what type of vector space they do live in, and mass, what type of fields. Usually for scalars, we have these sets that we call fields, what type of, fields that the mass lives in, and then acceleration, what properties this function has, and so on. So this statement is essentially the same way. So the first postulate of quantum mechanics, that are postulate one, or you can say axiom one, or you can say law number one. Law is a word that's generally not used for these, but it's equivalent in the same sense that we use to say about Newton's second law and so on. So this is that the state of a physical system is represented by a ray in a Hilbert space. That's why we had to study vector spaces, because a Hilbert space is a vector space, a special kind of vector space that has an additional property than vector spaces, that there is an inner product which is defined, and the vectors of this vector space. And the inner product, satisfy the properties of linearity, skew symmetry, and that the length of the vectors is a positive number. So that's why we spent the whole lecture on vector spaces. Okay, perfect. So today we will keep going and study the second law, you can say, of quantum physics. And let me give it the name Postulate 2, Axiom 2. And this axiom that I'm going to state is sometimes not written separately as an axiom. In some books, you wouldn't see this there, but you'll appreciate that this, in fact, is one of the assumptions when we are studying quantum mechanics, and that is that all observables are represented by self-adjoint operators. By the way, when we have finite dimensional Hilbert space and operators are all bounded, that they we'll see what we mean by bounded, but roughly seen that when you apply this operator on some vector in Hilbert space, you don't get infinity. Okay, the norm of the resulting vector is less than infinity. It's a number which is not infinite. In that case, self-adjoint really mean Hermitian. And since in quantum information theory we are concerned with systems that have finite number of levels, इस course के अंदर mostly we will be concerned with two-level systems which we call a qubit. But even if you extend the theory to D-level system, where D is a finite number, even in that case, since we have finite number of levels, then self-adjoint and Hermitian, they mean exactly the same. But this is sort of a more general statement than this one. So self-adjoint operators. This is the second law of nature. Okay, so I'm saying the word law just to emphasize the importance of this, axiom and postulate, because this is what we think how universe behaves. That the observables, the quantities that we can measure, okay, they are represented by Hermitian operators. We don't know yet why, but that's how the case. So since today we have introduced another postulate that now require us to define operators, their properties, and also what is the Hermitian operators and all sort of machinery that goes along with this. So today's lecture would mostly be about operators. And from this axiom of quantum physics, we see that why the study of operators is an important and integral part of a physics class. Simply because all physically important quantities, they are represented by Hermitian operators, so we have no choice but to study operators. So today's lecture is actually going to be mostly about operators, but we'll, of course, since these operators are defined over vector spaces, so essentially both of these topics we will cover today. And I just want to give a comment on the thing that we were talking in the last class about a special vector space of matrices. Usme, I was confused about the product कौन सी है. So basically, वो जो vector space है, it's called the Frobenius vector space. Sometimes it's called Hilbert-Schmidt vector space. Sometimes it's called Schur vector space. Sometimes it's just called trace space. Because and I have actually given a problem on that in homework, so you will know that what that Hilbert that specific vector space is. जो मैंने वो product matrices के लिखी थी जिसमें we had corresponding elements multiplying each other, that's not the definition of inner product space for that one. That's a Hadamard product of matrices, and that had nothing to do with that vector space. So I hope the homework question clarifies that thing. Okay, so today we will spend the entire class on discussing the operators. And just to make sure, the homework 2 is out and the submission date is Monday. It's mostly based on vector spaces and operators, what we are going to cover until today. Okay, so an operator, you can think of it as something as which takes a vector in a vector space V and takes it to the same or another vector space, let's say W. So this is an operator. Both of these, vector spaces can be different and they can be same. So it can take the vector from the same vector space and back to the same vector space, or it can take the vector and take it to the other vector space. For example, this might be a 2-dimensional vector, this might be a 10-dimensional vector, or vice versa. Okay, so, and let's now define the self-adjoint or Hermitian operators. And before that, let's define the adjoint of the operator. So adjoint of the operator is, let's say we have an operator A, and this is some vector phi, and this is some vector psi, and both of these vectors, let's say, lie in this vector space. Then, or actually, this can be different from this vector space, because suppose this is a 2x3 matrix, then this psi would be a 3x1 vector, and this phi would be a 2x1 vector. So this phi and psi, they can belong to two different vector spaces. And this A transforms actually this psi from, let's say, this vector space V to a vector space phi. Actually, let me use the convention that I have specified over there. So suppose this vector operator A applies to vector V, and then we take the inner product with some vector W, and we get some number, because it's an inner product. Then, and by the way, today I'm using the usual notation. Instead of writing this notation, I'm using this one. So they exactly mean the same thing. So adjoint, we define it to be like this. It's an operator that if we operate it, let's say on W, and then takes inner product with V, we get the same number. Okay, so let's say this is a 3x1 vector space. So suppose this is, अभी देख लेते हैं. So suppose this is a 2x3, 2, 3, 1, and this is I don't know, some 1, 2 vectors. So these are 2-dimensional vector space, a 3-dimensional vector. Let's say my operator is 1, 0, 1, 2, 1, 6. Now, when I operate this A on this, I'll get a vector which is 2x1. Then I'll be able to take an inner product. Make sense? Okay. So I think the confusion is because you are mostly used to working with the square matrices as operators, but the operators doesn't have to be a square, right? So unless it's an information conserving operator, we can't say that it can't add or cannot add information. नहीं, इसका देखें इनवर्स उस तरह से तो होगा भी नहीं जिस तरह हम आइडेंटिटी आप इसका वो ट्रांसपोज फाइंड करें, and there's a possibility what we call sort of pseudo inverse, that we can find an operator that can take us back here. Why not? Okay, so the operator doesn't, the point is the operator doesn't have to be something that takes a vector from one vector space and brings it back to the same vector space. The vectors can be non-square, the operators can be non-square, okay, and they can take a vector from one vector space and take it to the other vector space. In general, That's it. There's no restriction on these to be, that they have to be in the same vector space. बस ये मैंने अब इस तरह से लिख दिया कि ये इसको इसमें लेके आ रहा है. नहीं, जैसे इस एक मैं इस पे अप्लाई करूं तो क्या बनेगा? ये 2x1 वेक्टर नहीं मिलेगा. So you'll have something here and something here. So ये 2x1 वेक्टर है. तो फिर ये तो इस पे अप्लाई नहीं कर सकेगा. कोई बात नहीं, वो किसी और में चला जाएगा. हाँ, तो पॉइंट असल में ये है कि ऑपरेटर जो है वो एक वेक्टर स्पेस के वेक्टर पे ऑपरेट करता है और जो रिजल्टिंग वेक्टर है इट कैन बी इन अनदर वेक्टर स्पेस. मतलब जो भी होगा वो उसकी वो रेंज होगी ना. हर ऑपरेटर की एक डोमेन वेक्टर स्पेस है, एक रेंज वेक्टर स्पेस है. दे कैन बी बोथ डिफरेंट. ठीक है जी जी. और जो फिजिक्स है इस पे दे आर वेरी कॉमन. फॉर एग्जांपल मेजरमेंट ऑपरेटर्स, दे आर ऑल लाइक दिस. दे आर हर्मिशियन ऑपरेटर्स. दे टेक let's say a vector space in multi-dimensional space, and when you do a measurement the state is projected to a vector space that usually have a smaller dimensionality than the whole bigger vector space. So it's not uncommon or useless. हाँ, अभी तो ये हर्मिशियन नहीं है. ये हर्मिशियन नहीं होगा तो ये ऑब्जर्वेबल भी नहीं है. हाँ, तो कोई बात नहीं, हमने अभी हर्मिशियन को डिफाइन भी नहीं किया. सो दिस इज अ जनरल ऑपरेटर. ओके, सो सारे ऑपरेटर जो हैं वो हर्मिशियन नहीं होते. हर्मिशियन ऑपरेटर सिर्फ it's a very small class of operators that is Hermitian operator. Okay, all right. And okay, so we have this, and so यहाँ पे मैं adjoint को define कर रहा हूँ. So adjoint is something, या इसको अगर आप यूं लिखना चाहें, so adjoint operator इस तरह से define करते हैं कि इसको आप दूसरे वेक्टर पे अप्लाई करें और फिर इसके साथ इनर प्रोडक्ट लें, you get the same number. So this is what we call an adjoint of the operator. And self adjoint operator वो होता है, self adjoint operator is an operator such that A is equal to this AA. In general, the operators have a different adjoint. Okay, but there are some operators that their adjoint is the same as the operator itself, and that operator we call a self-adjoint operator. And yeah, इसको Hermitian भी हम कहते हैं. All right. So, and we'll see that why this axiom is there, why a Hermitian operator in a little while. Okay. So let's now see the matrix representation of operators. In general, operators don't have to have a matrix representation. Okay, especially a finite dimensional representation. We can have infinite dimensional a matrix representation for operators. For example, position operators or momentum operator, d by dx, and so on. There are many types of operator for free particles that you need infinite dimensional vector spaces. and infinite dimensional matrices. But for many matrices, for many operators, we can have a finite dimensional matrix representation. So let's try to establish a link between the two. So matrix representation of operators. Okay, suppose we have an operator A which acts on a vector space V and takes us to a vector space W. And suppose that this vector space is n dimensional and this vector space is m dimensional. This is my notation for saying that this is an n dimensional vector space and this is an m dimensional vector space. Now, it means that this vector space has a basis which has n linearly independent vectors at most. So the dimension actually is defined as the number of vectors in the basis that can represent all vectors in this vector space. So अगर ये n dimensional है, इसकी basis में n vectors होंगे. If this is m dimensional, then this has a basis that has m vectors. Okay. So suppose I want to find out that what happens to a vector v, a general vector v in and when I operated with operator A and I get some vector w. Okay, so for that all I need to know is what happens to the basis vector of this vector space. क्यों? क्योंकि कोई भी vector जो है general, that can be written as a linear superposition of the basis vectors alpha n vn, right? Some इसको अब यूं भी लिख सकते हैं alpha n vn. So for this transformation to work out, all I need to work out is what happens to this, individual basis vector. So for that, let me take some, ith vector and operate it with this operator A. And suppose I get some, vector w dash. And let's actually write some, I here, because when I is 1, I get w prime 1, and this, w1 prime is not necessarily w1. In fact, this itself could be a j1 to m, a ji. So this vector is a linear superposition of these basis vectors. So no dash here, wj. ये नहीं, ये ऑपरेटर नहीं, ये तो कोई स्केलर नंबर है, ए जे आई है. सो ये ऑपरेटर है, दिस इज सम स्केलर नंबर. इसको फॉलो करें. ये मैंने जस्ट ये लिख दिया है कि ये जो वेक्टर जो भी हमें मिलेगा ith बेसिस वेक्टर पे ऑपरेट करके, दिस इज सम लेट्स से a1i omega 1, a2i omega 2 all the way to a mi omega m. और ये मैंने i सबस्क्रिप्ट इसलिए रखा हुआ है कि डिफरेंट जो बेसिस वेक्टर है इसके, उनके ये कोफिशिएंट इन जनरल डिफरेंट होगा क्योंकि ये वेक्टर डिफरेंट होगा. Now all I need to find the transformation is work out what these numbers are. और अगर इन नंबर्स का आपको पता चल जाए ना कि what are AJI, then next time आपको कोई भी वेक्टर मिले इस वेक्टर स्पेस के अंदर और आपने यहां पे वेक्टर फाइंड करना है ऑपरेटर ए ऑपरेट करके, all you need to know is only these numbers, right? ठीक है मनी? क्यों? क्योंकि इसके अंदर कोई भी वेक्टर जो है उसको मैं लिख सकता हूं सम ऑफ दीज बेसिस वेक्टर. और अगर मुझे ये पता चल गया कि हर एक बेसिस वेक्टर पे ऑपरेटर किस तरह से ऑपरेट करता है, ये नंबर क्या है, अगर if I know all these numbers, I know the action of this operator completely. So let's now try to find these numbers. So A V I J A J I, and for that we can exploit the orthonormality. Assume that these are the orthonormal bases. Then if I, let's say, take the inner product with some V, let me call it K A V I A J I. Actually, let's use the W here. Now this product is delta Kj because these are orthonormal basis vectors, and so it means I get A K I omega K A V I. So this is now the relationship of our operator with the elements of a matrix, because I can construct a matrix A with elements AKIs, where K goes from 1 to M and I goes from 1 to N. So this is an M by N matrix. And the elements of my matrix are given by this relationship. All I have to do is figure out the action of operator on the basis vectors and take this inner product to find these operators. You might have seen this relationship earlier, but most likely for an operator that takes a vector from a vector space and brings it back to the same vector space. In that case, if V is the same vector space as W, then they both have the same orthonormal basis. So this essentially transforms to VK A VI AKI. But this is only a special case. This is the general case. So any question? And you can actually picture this these AKIs are like this. So let's say this is vector space V. This is vector space W. अच्छा, इस कोर्स में I'll try के आपको as best as I can and for as many things as I can try to give you a geometric picture. And there might be several homeworks as well in which I will have questions asking you to come up with a geometric picture. So the thing will work like this, because that helps us build intuition for many mathematical results, that we will be working with, of course, general Hilbert spaces, which mean that they are complex vector spaces, and we can't really even draw vectors in them. But if we specialize a Hilbert space to, let's say, a 2 or 3 dimensional Euclidean space in which everything is real, then I can represent these vectors by these geometric vectors that you see drawn in the books, and that can give us sort of an intuition what the result is saying. So that's something that I'm going to try to do here, and there might be some questions. For example, there's a problem on Cauchy-Schwarz inequality proof. The proof is, by the way, given in the Nelson Chuang as well, if you can find it. But there's an additional thing that I have asked you to come up with a geometrical picture for that inequality. And that's the same thing that I'll try to do in this course as well. Okay, so you can imagine these AKJs as, let's say, there is this basis vector Vi. It's being converted to basis vector. Let's say this is V1. It's converted to W1. There's this element A11. V1 being converted to V2. There's this element A21, and so on. So These numbers are telling us the transformation or the coefficient for converting a basis vector in the V space to the W space. And with this, we can make a connection of our operator with the matrix notation. And that's what we are now going to do throughout the course. And since we are going to work with finite dimensional quantum systems in this course, all of our matrices would be finite dimensional matrices. And we will be working with bounded operators, which mean that all of these numbers are bounded, that they are less than infinity. So that's why the word self-adjoint and Hermitian, they mathematically have the same definition. The difference comes when there are, just as a comment, because this thing is skipped in most of the books. So people start wondering, why do we even, study self-adjoint? Sometimes it happens that you have a Hilbert space, and for some of the vectors, the operator gave you infinite numbers. So then you restrict the domain of the operator to have to work it only on a subspace of the bigger vector space. And in this case, then we call it a self-adjoint operator, and it's Hermitian only when the domain is the whole vector space. But anyway, we're not going to worry too much about this distinction. Okay. So any question regarding this? So now the adjoint operator for matrices is essentially, in the matrix language, adjoint of an operator is the Hermitian conjugate, which means that you take transpose and you take conjugate as well. Some actually books would write with an H as well instead of a dagger, but we'll be using this symbol mostly. So an adjoint of a matrix is this thing. It's a transpose conjugate. And when we say it's Hermitian, it means it's self-adjoint, which means that the operator and its adjoint is the same. And the reason for linking observables to Hermitian operator is that they have real eigenvalues, which mean that which make sure that all physical quantities, they are real numbers. They can be positive, they can be negative, they can be zero, but they will remain real numbers. Okay, but the self-adjoint or Hermitian operator even though for postulate 2 we only require these operators, but as we move forward, we'll see that we need a few other types of operators as well, which I'm going to work just today, because we are working with operators, so that when we state those axioms, we'll have the mathematical machinery a little bit before the statement. Okay, so another type of operators that we are going to be using in this course is what we call projector. Generally, people just use projector, which means projecting operator, but sometime people would also say projector operator, but that's a little bit of a tongue twister. So this essentially has both words inside it. So it's projecting or operator. And this will be important when we study the measurement theory. And this is an operator that works like this. So let me start with a geometrical interpretation first. Suppose you have a Hilbert space, which I'm now just drawing as an Euclidean space. So you have the state of the system somewhere in general, anywhere inside this vector space. A projector operator is a special operator which projects the vector into a subspace of this bigger vector space. And that subspace is specially defined. For example, I want to project this state into this XY plane. So then my operator, when it operates on this vector, this will give me a vector which lies in the XY plane. There might be, other ways to define it as well. But if I'm working with the three-dimensional vector space, I can define this type of projector like this. As you can see that this matrix, first of all, it's Hermitian, right? Now, this time what I have done cleverly, that instead of just, keeping it until here, I've just put a row of zeros that had made it square, that had made it Hermitian as well. But we can see that essentially our three-dimensional vector, when I operate it on some x, y, z, I get x, y, and 0. So a vector which is lying in xy plane has a z component 0. And effectively, it's an operator which is taking a vector in three-dimensional vector space to two-dimensional vector space. But mathematically speaking, the way we have defined the projector and the way we have written the vectors, this is still a three-dimensional vector space because this, has a three, and this is still part of the three-dimensional vector space because I'm not just writing x, y, I'm writing x, y, z, even though z is always 0. So which means G. Projector, it's a projector operator. So in general, no, you have to be careful here because then this operator has this property that it's projecting to a vector space where the component of this vector in that vector space are not changed. If you, let's say, have a projector 2 to 0, you will get a vector which is like this. So now it has the same direction as the projection itself, but it has double the magnitude of the projection. Okay, so if you have minus somewhere, you might project it to some other direction. So it's not an arbitrary projection, it's a special projector operator that preserves the magnitude and direction in the subspace. Okay, and we can easily see that if a vector is already in the xy plane, our projector shouldn't do anything to it, which means that if I have already obtained a vector by projecting from somewhere else, if I project it again, I'll get the same thing. So p square is actually equal to p. Even p cube should be equal to p, or any n greater than 2 should give us the same thing. So once we have projected, projecting again doesn't do anything to the vector. And we can see from this matrix notation as well, if I multiply it with itself, I'll get the same matrix. Okay, there's another related and important operator. It's also an projector operator, but it projects to orthogonal space. Projector to orthogonal vector space, which means that if I have a projector P, and instead of projecting to its vector space, I want to project it into a vector space which is orthogonal to it, then I use this operator I minus P. Okay, which means over here, if I operate it with the P, I get this thing. This vector was P V. And if I operate it with Q, I get this vector, which is orthogonal to this vector space. So this is my Q V. You can say that okay, if we have to project it along this thing, why we can just use this another projector 1 0 0 0 0 0 0 0 1 instead of defining this convoluted way of I minus p, right? But I'm doing it because this intuition is easier to work in this three-dimensional space, and I can quickly write projector. But when we have a higher dimensional complicated vector space, it sometimes might be easier to be defining projector using this I minus p notation as well, because we might have, let's say, a 10-dimensional vector space, and we are trying to write the component of our vector in two orthogonal vector spaces. So orthogonal vector spaces are the vector spaces that the two vectors from those subspaces, when you take a dot product, inner product between them, you get 0. So this helps us to project to orthogonal vector spaces, because sometimes we have to work with components of vector spaces like this. Okay. There's another operator that I would like to define right away. अगर आप किसी पॉइंट पे बोर होने लगे ना कि ये चीजें हमने की हुई हैं, so you can just let me know. I can skip it over. क्योंकि थोड़ा सा rudimentary है. So, and this is the unitary operator. So unitary operator is this special operator that the Hermitian conjugate is actually the inverse of the operator, which means that u dagger is identity, or u dagger u is identity, and this has this nice property that its eigenvalues are all such that its magnitude is 1. I'm not going to prove it up. Proof kiya hoga, ya you can check the proof at any place. So कोई बंदा ऐसा है जिसको आइगन वैल्यू आइगन वेक्टर की डेफिनेशन का पता ना हो? क्यों अली रज़ा? You know what eigenvalues eigenvectors are? Okay, good. क्यों हैदर आपको आइडिया नहीं है eigenvalues eigenvector क्या होते हैं? अच्छा ठीक है. कोई ऐसा बंदा जिसको ना पता हो? मुनीब? You understand? Okay, good point. So इसका मतलब है कि you can write all of these eigenvalues something like this, exponential iota theta as well. क्योंकि any complex number with magnitude 1 can be written as exponential iota theta. So I did mention जो Hermitian operators हैं, their eigenvalues are real, but their magnitude may not be 1. It can be 1, but it can be other than 1 as well. क्योंकि इसकी मैग्नीट्यूड 1 होती है ना. तो अगर ये आपके पास कोई भी कॉम्प्लेक्स नंबर, ये कॉम्प्लेक्स नंबर्स है ना, ठीक है, तो कॉम्प्लेक्स नंबर्स वो होते हैं जिनकी मैग्नीट्यूड, यहाँ पे आइगन वैल्यूज सिर्फ वही एडमिसिबल हैं जिनकी मैग्नीट्यूड 1 है. ओके, व्हिच मींस दैट आई कैन राइट दीज कॉम्प्लेक्स नंबर्स लाइक दिस, क्योंकि इसकी मैग्नीट्यूड देखें 1 है. इसको यूं करके लिख सकते हैं ना, cos थीटा प्लस आयोटा साइन थीटा. तो इसकी जो मैग्नीट्यूड cos स्क्वायर प्लस साइन स्क्वायर वुड बी 1. ठीक है. Okay. Then there's another type of operators which we call normal operators. Normal operators are operators that satisfy this property. जरूरी नहीं कि ये आइडेंटिटी के बराबर हो, okay? But a dagger and a dagger a, they are the same. So इसका मतलब है जो unitary operator है, you can see they're also normal operator. Hermitian operator, what do you think? They should be normal operator or not? They should be normal operator, क्योंकि Hermitian में ये वैसे ही इसके बराबर होता है. So a is equal to a anyway. So Hermitian operators are normal operators. Unitary operators are normal operators. What about projector operators? They're also normal operators. क्योंकि p स्क्वायर वैसे ही p के बराबर है और their Hermitian operator p is equal to p dagger. So it means projector operators are also normal operators. Basically, all operators of interest in quantum physics, for us, they are normal operators. Projector operators, unitary operator, Hermitian operators, they're all normal. So this is sort of one unifying property of these operators. So any mathematical theorem that you prove for normal operators is going to be applicable to Hermitian, unitary, and projector operators. But not the vice versa. Something might be true for Hermitian operator, may not be true for normal operator, because normal operators include unitary operator as well, and other operators. They're actually, and okay, good question. Thank you. So let's say this is a vector space and there is this vector v. So when we apply the unitary operator to this vector v, this will this can go to, let's say, this place. So this changes, the vector changes because it's being operated by an operator. But since we have seen that the magnitude of eigenvalues is 1, what it does, it preserves the norm of the vector. जितनी भी vector की length यहाँ पे है, उतनी ही length यहाँ पे है. And we can check it. For example, let's say this is some vector w. Now w का अगर आप inner product लें, so this w is equal to v u dagger, and this w is u v dagger. But this is identity. So it means after operating with the unitary operator, the norm of the vector hasn't changed. And if your initial vector is normalized, your later vector is also normalized, which means that a ray is transformed to a ray. Next, let's state the next axiom of quantum physics anyway. So axiom 3, the evolution and actually sometimes there's a synonym word which is called dynamics of physical system is described by unitary operator. And just to be totally explicit, these axioms, as I have said in the last lecture, they're applicable only to closed quantum systems, not to open quantum systems. If your quantum system is interacting with the environment or something else, then these axioms are not true. But for an isolated quantum system, or you can say for a closed quantum system, these axioms are true. So it means that whenever you have some state psi at time t is equal to 0, after some time t, your state is described by an action of a unitary operator. And which means that the norms of the rays is always 1 for a closed quantum system. And that's one reason that we are studying these unitary operators. नहीं ओपन सिस्टम में क्यों वैलिड होंगे? नहीं, लेकिन पहली बात यह है कि एट द आउटसेट आप लॉजिकल आर्गुमेंट्स कर सकते हैं दिस शुडंट बी ट्रू. वो ऐसे कि लेट्स से मैं यहाँ पे हूँ, ठीक है, ओपन सिस्टम मीन दैट देयर आर अदर फोर्सेस दैट आर एक्टिंग ऑन मी. सो I know चूंकि it's the axiom which is coming later, but we know that the psi is related to the probabilities of finding things or the magnitude of physical quantities. अगर आपने कोई observable देखना है कि मेरी energy कितनी है, momentum कितना है, you apply an appropriate Hermitian matrix, and then you know. अब since I'm interacting with the outside world, हो सकता है कुछ देर बाद मुझे कोई बंदा वैसे ही यहाँ से बुला के ले जाए. So जो पहले तो ये था कि इस रूम के अंदर मेरे होने की probability 1 थी, यहाँ पे होने की let's say half है, यहाँ पे होने की half quarter है, यहाँ पे कुछ थोड़ी सी, but you add all up, it's certain time here. If this is a closed room, अगर if it's open, it's interacting with them, हो सकता है मैं वैसे ही यहाँ पे ना हूँ. So how can this be true for open system? Get the point? हाँ तो फिर तो वो क्लोज सिस्टम के अंदर मैं इधर हूं या कमरे के उस हिस्से में हूं या आप पूरी बिल्डिंग को एक क्लोज सिस्टम कह लें तो देन इट्स ओके. सो दिस इज वैलिड फॉर द टोटल क्वांटम सिस्टम, एंड एक्चुअली यूजिंग दिस we can then this course is going to be concerned about using this law, these 5 axioms, and trying to make sense of behavior of systems interacting with other systems, because we know the axioms for the whole our big our composite system. We will try to make sense of the parts of the system. That's what quantum information is all about. Okay. बल्कि आज ही मैं एक जो है ना वो पेपर देख रहा था from a couple of years ago that they had modeled like the whole universe as a quantum system. In fact, whole universe is a quantum system, and then 2 parts of it like interacting with each other like 2 open systems. So agar aap bigger scale pe dekhe, then of course the whole universe is one closed system. So in a way, these axioms are actually only valid for the universe as a whole, kyunki practically speaking everything else jo hai, it's just part of the universe, so everything is interacting with something else. So these axioms, they are only approximately true for practical systems. They are as true as you can isolate your system from the rest of the world. Okay, any other question or comment? No. Now we are going to discuss an actually very important theorem, and I'm not going to prove it in general. I'll just explain its use and intuitive sort of proof, but you can check the proof in Nelson and Chuang books if you like. So this is related to the decomposition of an operator. So this particular is called spectral decomposition, yeah, you can say representation of normal operators. So now you know at the outset whatever is the statement of this theorem, if it is proved, it's going to be applicable to all normal operators, including Hermitian, unitary, projector operators. Okay, so the statement is this, that normal operators can be diagonalized. In some basis. So the theorem doesn't say okay which basis, but it does say that every normal operator can be diagonalized in some basis. If we saw that when we were connecting the operator with the matrices, that we can find the components of the matrix using the basis of the both vector spaces. And this theorem says that if your operator is normal, then there exists a basis with respect to which the corresponding matrix is diagonal. Okay, and it actually has a reverse in itself as well. All diagonalizable operators are normal. So I'm just going to prove the simple part. This proof you can check there. So this is easy. If your operator is like this, right? So only elements are on diagonal. Then its conjugate transpose is going to be like this: A star, B star, C star, right? Because when you take transpose, since you have elements only on the diagonal, and since this implies that a dagger is a dagger, we can easily check. आप इसको इधर रख के मल्टीप्लाई करें, उधर रख के करें, जो रिजल्टिंग मैट्रिक्स है उसके डायगोनल पे आ जाएगा a mod square, b mod square, c mod square, and so on. So if they are diagonal, they are normal operators. The converse, you can check the proof there. It's a little bit involved, and I don't think it's the proof is needed for what we want to do. But I'm going to, sort of give you the geometric viewpoint of this decomposition. Suppose we choose, we have an operator, a normal operator, and it has eigenvectors lambda n and eigenvalues lambda n. So these are eigenvectors, these are eigenvalues. Now, let me draw this Euclidean vector space G. जी जी जो स्पेक्ट्रल, अभी आपको पता चलेगा इसका नाम ये क्यों है, बट यहाँ पे जो पॉइंट लिखा हुआ है इससे नहीं पता चल रहा कि व्हाई इट्स कॉल्ड स्पेक्ट्रम. ठीक है, यहाँ से बस ये पता चल रहा है कि जो डायगोनल ऑपरेटर्स हैं दे आर नॉर्मल. ठीक है, और ये भी प्रूव किया जा सकता है जो नॉर्मल ऑपरेटर हैं दे कैन बी डायगोनलाइज्ड. ठीक है, लेकिन इस थ्योरम से जो ना ये पता नहीं चल रहा कि इसका नाम स्पेक्ट्रल डीकंपोजिशन क्यों है. ओके, दैट्स गोइंग टू बी अपरेंट फ्रॉम दिस एक्सप्लेनेशन. मैं बिकॉज we can actually diagonalize these operators in its eigenbasis. And चूंकि काफी क्वांटम फिजिक्स से भी पहले से जो हिस्ट्री है क्लासिकल फिजिक्स की, उसमें जब हम जो आइगन वैल्यूज हैं उनको स्पेक्ट्रम भी कहते हैं. So that's why it's the theorem's name is now spectral decomposition. ठीक है, so word spectrum usually in physics means the eigenvalues. स्पेक्ट्रम जो है ना उसका मतलब कहता है आइगन वैल्यूज. सो किसी ऑपरेटर की अगर मैं आइगन वैल्यूज लिखता हूं तो आई कैन से ओके दिस इज द स्पेक्ट्रम ऑफ दिस ऑपरेटर. ओके, सो सपोज वी हैव एन ऑपरेटर विद आइगन वेक्टर्स एंड आइगन वैल्यूज लाइक दिस, एंड let's say I write my operator A as a superposition of some other operators Pn. Okay, so this is general operator, and now I have expressed it as some of the superposition of actually projector operators. And what are these projector operators? These projector operators are like this. These are special projector operator. Each one of these operator projects my general vector V onto the one-dimensional vector space spanned by the corresponding eigenvector. So this is important. So this is a projector operator which simply gives me the component of my vector V along one of the eigenvectors. So जैसे इसको अगर आप लिख लें A1 P1 plus A2 P2, and these are some scalars which we will find later. But these operators are operators that project any vector along the given गिवन आइगन वेक्टर। मैं आपको एग्जांपल देता हूँ। फर्ज करें ये आपकी आइगन स्पेस है, ये 3 डायमेंशनल वेक्टर स्पेस है, एक्स वाई जी। एंड फर्ज करें कोई ऑपरेटर ए है और उसके आइगन वेक्टर्स हैं, और मैं उनको नॉर्मलाइज भी कर लेता हूँ आइगन वेक्टर्स को। फर्ज करें कि ये लैम्डा 1 है, ये कोई लैम्डा 2 है, और ये कोई लैम्डा 3 है। जरूरी नहीं कि तीनों में से कोई एक या दो या सारे बोर्ड की प्लेन में हो, दिस आर 3 डायमेंशनल वेक्टर स्पेस, बट वेयर एवर दे आर समथिंग लाइक दिस। ये जो P1 ऑपरेटर है, जब मैं इसको इस V पे ऑपरेट करूंगा, दिस विल गिव मी इट्स कंपोनेंट अलोंग दिस आइगन वेक्टर। ये जो P2 प्रोजेक्टर ऑपरेटर है, दिस विल गिव मी अ कंपोनेंट अलोंग दिस सेकंड आइगन वेक्टर, और जो P3 है, दिस विल गिव मी अ कंपोनेंट ऑफ दिस वेक्टर along this third eigenvector. So each of the projector operator gives me the component of the vector along the particular eigenvector. This is my projector operator. So I have expressed my operator as a superposition or a linear combination of these projector operator, where each projector operator is projecting along one of the eigenvectors of my operator. Okay, so this first of all means this thing. That these operators are orthogonal in the sense कि चूंकि you can actually show कि जो नॉर्मल वेक्टर, जो नॉर्मल ऑपरेटर है, उसके जो आइगन वेक्टर्स हैं वो ऑर्थोगोनल होते हैं। सिंस ये सारे वेक्टर ऑर्थोगोनल हैं, तो इसका मतलब है ये जो तीनों वेक्टर्स हैं, दे स्पैन ऑर्थोगोनल वेक्टर स्पेसेस। सो आपने जो 3 डायमेंशनल वेक्टर स्पेस है, इसको 3 1 डायमेंशनल ऑर्थोगोनल वेक्टर स्पेसेस में हमने डिवाइड कर दिया। एंड ईच प्रोजेक्टर प्रोजेक्ट्स टू a vector space which is orthogonal to the other two. इसी तरह अगर 10 dimensional vector space है, so each projector will be projecting to 1 dimensional vector space where all of them are orthogonal. So this means this, कि my projector operators are orthogonal. If n and m are same, I get this p square is p, right? If n is equal to m, then I should have p square is equal to p, which is the property of projector operator. And when n and m are different, I get 0. So which means that if I have once projected a vector along this, अगर इसको मैं इधर के along project करूंगा तो आंसर 0 होगा, because this doesn't have any component along this and this vector. Okay, so I have decomposed my operator as a combination of projector operators along each of the eigenvectors. And since these projector operators have to be Hermitian, we can infer that the projector operator is this. This operator we can see projects any vector v along a given eigenvector. क्यों? क्योंकि अगर इसको मैं ये अप्लाई करूं इस वाले वेक्टर पे, let's say p1, so let's do it here. So when p1, which is lambda 1, this is p1, when you apply this p1 on v, what we get is this lambda 1 v. So this is some number, let me call it some v1 lambda. So this projector operator projects along a given eigenvector. All right, so using this, now I can rewrite this operator A as sum of an lambda n lambda n. Now all I have to do is find these ans. So this is very easy. What I can do is pick this vector A, this operator A, and operate it with some lambda m, some lambda k, And over here I have sum over n, an, lambda k, lambda n, lambda n, lambda m, and I get an, delta kn, delta nm, and the answer is equal to so this is delta, so this is delta, and this k has to be equal to n, and I get this n has to be equal to m, and let's see, this is bn. Okay, and yeah, so k has to be equal to n and n has to be equal to m. So this is, let me write it am, and here I have lambda m, a lambda. So the coefficient of this spectral expansion are given by this. Now our representation is complete. Any normal matrix can be represented as a superposition of like this. And if you look at it, this is a diagonal matrix like this. A1, A2, all the way to whatever is your, let's say, dimension is 1 to D, KT. This is 0, this is 0. So this is the representation of a diagonal matrix. You can find, the coefficients. Because यहाँ पे lambda n है. When you take its inner product with vectors that are not equal, answer would be 0. So now we have shown that in the eigen basis of an operator can be diagonalized. So, and it's called a spectral decomposition because the eigenvalues are usually referred to as spectrum. And this is an extremely important representation. Actually, most of the operators that we will study, we will frequently be writing them in the eigenbasis. उसका असल में फायदा बहुत होता है. जो mathematics it becomes extremely easy to apply any operator, on some vector. All we then have to do is express that vector in terms of the eigenvectors of the operator, and then we quickly know किस operator का action उस vector पे क्या होगा. ठीक है? क्योंकि सब कुछ हम कर किस लिए रहे हैं, ये अपनी सहूलत किस लिए कर रहे हैं कि invariably we will have to be evaluating this operation, that there's a vector and there's an operator, we want to find out what we get. So the usual way would be you write this v in terms of let's say some vi lambda I. So I can express this vector as a superposition or a linear combination of eigenvectors of this operator. And after that, life becomes easy because we know the eigenvalues corresponding to each of this operator. So we can multiply this one like this. This is equivalent to saying that this A is like this. So that's why this spectral decomposition is easy. And let me give you spectral decomposition for the simplest operator. Identity operator. So this is an operator. For example, in 3 by 3, this operator would be 1 like this. This is an identity operator. और अगर आप इसके eigenvectors find करें, by the way, तो you'll get these. Let me call this eigenvector 1, this eigenvector 2, this eigenvector 3. So I can write it like this. Yeah, इसको यूं लिखें. So this is the identity operator. And this is sometimes actually is also called the completeness relation. When you generalize it to, any vector space. So this then is, let me write it some vi, where, these v's are it can be an orthonormal basis for a given vector space, which in many of the vector spaces we can think of these 1 0 0 0 1 0 0 0 0 0 1 type of vectors as orthogonal vector. We can call them like this. So this is the relation that we sometimes also refer to as the completeness relation. And it's called completeness relation because if we have a vector space, and if the vector space has an orthonormal basis, so that every vectors in that vector space can be written as a linear combination of those eigenvectors. It means that all of those basis vectors are part of this. And this is the basis is complete in a sense that any vector can be written as a linear substitution of those vectors. Okay, any question on the spectral theorem?
Sir,
Did you?
general vector in terms of projection operator किस तरह से लिखता है?
वो जनरल वेक्टर जनरल ऑपरेटर है। जी जी।
इसको आपने projection operator की टर्म में किस तरह से?
इसलिए कि आई मीन ये ऐसी है कि फर्ज करें आप अगर जनरल वेक्टर की बात करें 3D रियल स्पेस है, ठीक है, जो यूएल ये 3 डायमेंशनल स्पेस है, तो कोई भी वेक्टर है जो कि 3 डायमेंशनल है, तो वी कैन राइट इट एज अ लीनियर सुपरपोजिशन ऑफ इट्स 3 बेसिस वेक्टर, ठीक है। और ये जो हमने वो प्रोजेक्टर की फॉर्म में लिखा, दिस इज एग्जैक्टली द सेम थिंग। सो वी आर एसेंशियली सेइंग कि अगर आपके पास 3 डायमेंशनल वेक्टर है और उस पे जो ऑपरेटर है, कोई आप जिसको 3 डायमेंशनल में 3 एक वेक्टर है, उस पे कोई भी लीनियर ऑपरेटर होगा, वो क्या करेगा, इसको कहीं ले जाके 3D स्पेस के अंदर ही उसने रखा है ना। तो इसका मतलब है जो आंसर है वो भी एक वेक्टर है which has 3 components again along x, y and z axis. Okay, so it means कि जो एक्शन है किसी भी ऑपरेटर का, this can be represented as a combination of actions along each of the dimension. So it means the action of this operator A is actually just given by these numbers A n, where this is just specifying the basis. Okay, each of the number corresponds to each of the orthogonal dimension. Okay, so that's why we can write any operator, any normal operator like this. And these are actually just the eigenvalues. If you see like this is because this thing is nothing but an eigenvalue. This is an eigenvalue equation. Because this is an eigenvector. When you operate this A on lambda m, what we will get? We will get something into lambda m, right? And the lambda m dot lambda m is 1. So this am is actually lambda m. So you can equivalently write this thing as 1 to d lambda n lambda n lambda n. So to find the spectral decomposition of any operator, you only need to find 2 things: eigenvalues and eigenvector. You have a spectral decomposition. ये जो identity operator है, इसके eigenvectors हैं ये 3, और इनकी तीनों के eigenvalue भी 1 1 1 है. So that's why I have 1 और ये तीनों eigenvector बारी बारी. Remember, इसमें ये दोनों का index same है. ये I पे sum है and it's the same index. It's not 2 different indexes. Okay, so any other question regarding this? Okay, let me do. मैंने कहा प्रूफ उसमें चेक बुक में चेक कर लें। ये बात गिवन है कि वो हाँ हाँ जी। Okay, I just want to illustrate one application of this completeness relation. बल्कि ये आपने बल्कि काफी जगहों पे यूज भी करते होंगे. Usually you can substitute this identity anywhere you want. You are, for example, let's go to the next board. You have okay, something like this. then we'll go to the proof. So I wanted to prove Cauchy-Schwarz, लेकिन ये already आपको जो है ना उसमें दी हुई है homework के अंदर. So जो Cauchy-Schwarz inequality है उसका जो proof essentially rests on using this completeness relation, and we'll be using it many times. Right now, what I want you to do is take these papers. ये फलान सबको एक दे दें. And find the spectral decomposition of Pauli operators. Pauli operators जो है in 2 by 2. So let me write it. So sigma 1 भी कहते हैं इसको, sigma x भी कहते हैं. This is 0 1 1 0. And then sigma z. 1 0 0. So जो तीनों ऑपरेटर्स हैं इनके आप जो स्पेक्ट्रल डीकंपोजिशन है वो फाइंड करें. आइगन वेक्टर्स फाइंड करें, आइगन वैल्यूज फाइंड करें, और आप जो आइगन फैक्टर फाइंड करेंगे ज़ाहिर है जब आपने स्पेक्ट्रल डीकंपोज तो आपने उनको कुछ नाम भी देने होते हैं. ठीक है, जैसे इसको मैंने 1 कर दिया, इसको तो आप क्योंकि दो वेक्टर हैं 1 2 वाला यूज कर लें, बल्कि आप जो भी आइगन वेक्टर है उनको 0 1 यूज कर लें. नहीं 0 1 हम स्पेशल पर्पस आप 1 2 कर लें. ठीक है, लेकिन हर केस के अंदर लिखते हैं क्योंकि तीनों में इन जनरल यू विल हैव डिफरेंट आइगन वेक्टर्स. सो जस्ट राइट व्हाट दोस 1 2 आर. एंड बाय द वे ये ऐसे मैट्रिसेस हैं जो हर्मिशियन भी हैं, यूनिटरी भी हैं. Let me close the recording.